Assalamualaikum and good morning. Okay, we continue our discussion for topic Z-source inverter, Z-source or Z-source inverter. Okay, so yesterday we have discussed the advantage of using the Z-source, so where it can boost the voltage. So this type of inverter is widely used for renewable energy interface because solar panel, your solar array, the voltage produced is small, so means you need to boost the voltage. Okay, so this case, the voltage can be boosted by using the impedance. So mean you have combination of inductance and capacitors, where these two elements we classify as energy storage element. So by using this impedance network, then actually it can boost the voltage to be supplied to the terminal of the inverter. So this is the inverter, and so you have these two terminals, okay, plus and sorry, this one is plus, sorry, right, plus to minus. So where the voltage across plus to minus we define as V inverter, okay. Okay, then we have discussed also the maximum voltage can be produced by using these modulation techniques. And you have three here: sinusoidal, six-step, and space vector. So where the production of the voltage actually cannot reach to the VDC, beyond the VDC. So means these three types of techniques cannot fully utilize the input voltage of the inverter. So in order to increase the voltage, also to boost the voltage by applying the Z source, you need to modify the original circuit of the inverter by inserting the impedance network here in between the DC source and the inverter. Okay, then here we also compare the switching states operation for the conventional inverter using the sinusoidal pulse width modulation. So where the switching operation is complementary. And for the Z source, you have 7 additional switching state because the Z source allow top and bottom switches, any leg, to be turned on at the same time. Okay? So maybe you have a combination of maybe one leg, two leg, or all legs. So here, because of the impedance network, so the inverter allow, the switching operation can be turned on. Top and bottom switches can be turned on at the same time. And so because your DC source here is not connect directly to the inverter, because we have the impedance here. Okay, then we go for the circuit analysis because we need to derive some equation to verify that the capability of voltage can be boosted by using the Z source. So you need to draw these two equivalent circuit for two cases. Case 1 for non-shoot through and shoot through mode. So remember, for non-shoot through, the diode will be in forward bias and the voltage across the inverter will be V inverter. And so we can represent between these two terminals, plus to minus, as a current source. And because we assume that you put very large value of inductance, and so mean the current is constant. We consider the current is constant. And for the shoot through, the diode is in reverse bias. So mean here open circuit. So because of the leg of inverter is short, so mean you can represent the two terminals here as a short circuit. V inverter will be 0. And because top and bottom switches, one or more legs are turned on at the same time. So that's why here will be short. So then you need to apply this assumption in order to simplify the analysis, to derive some equation. Then here we analyze for two equivalent circuits here to obtain the inductor voltage and inverter voltage. For two cases, non-shoot through and shoot through. Then you need to apply this assumption where the average voltage across the inductor over one switching period will be 0. So you just multiply between the voltage, the inductor voltage and its time. So this one, inductor voltage during shoot through, then you have to multiply by sampling period. The shoot through period. For the inductor voltage for the case of non-shoot through, so you have to multiply with non-shoot through sampling period. Non-shoot through period. So where VL and the inductor voltage for shoot through and non-shoot through, you need to substitute using equation 1 for non-shoot through and 3. So this one is VC. Here will be difference between DC voltage and VC. So then you apply to this equation. Then you can obtain equation number 5. Okay. Then you rearrange the equation so that you get this relation. Then you need to obtain the equation of the peak of the inverter voltage. So you have to apply or use equation 2 and 6. Okay, 2 and 6. Okay, then here you finally you can obtain this equation. Okay. Then from the equation 2, so actually you can equate the term of the bracket term as G. G is the boost factor. G is the boost factor. So where here you try to rearrange the equation so that you get this equation. So this case, we can prove that when the value of G is always larger than 1, and it cannot be less than 1, because of this ratio. TSH divided by TS. So means that your your shoot through period should be smaller than sampling period, TS, right? So means this term should be less than 1. So then you subtract with 1. So actually for this fraction, the denominator of the fraction will be less than 1. So mean G should be larger than 1. So this is how we prove. G value cannot be less than 1. It always larger than 1. So this is the boost factor, G. And then we know that for the the conventional inverter using SPWM technique. So the fundamental you can calculate using this equation. So the maximum voltage can be produced is half of VDC, VDC divided by 2. So applying this equation, so you can notice same pattern for the Z source here, right? But the VDC you need to substitute with inverter voltage, V inverter voltage. So then peak of the inverter voltage, V in peak, because this term V inverter peak of the inverter is the input voltage of the inverter. It's not the VDC, because you have the impedance in between the DC source and the inverter. Okay, clear? Same pattern with the conventional inverter using SPWM, but for the conventional, the term here is the VDC, but for the Z source is V inverter peak. So we know that the V inverter peak is multiplication between G and VDC. So you have additional term G here for the Z source. So this term play important role to boost the voltage, because you need to take into account that the G always larger than 1. So you can play around the value of G in order to obtain the desired voltage. Okay, clear? So mean you can control the voltage to get the desired voltage. So you have two options. One, by adjusting the MI, the motion index. So another one is adjusting the value of G. Okay, clear? So this is the advantage of using the Z source. Okay, so for today we proceed. Actually, today's class, we try to relate what we have discussed yesterday, how the equation, the boost factor, we can implement. We can implement the equation for modeling the Z source inverter. So sekarang maksudnya today's class, we try to understand how to develop the simulation model of the Z source. We try to relate the equation that we have derived yesterday so that we can implement to model the Z source inverter. Okay. Okay, so first of all, we look at the conventional inverter using sinusoidal pulse width modulation. So you have three-phase modulating signal. So this is, the red color is VA, yellow is VB, the blue is VC. So remember the modulating signal as the reference signals. So where the signal are balanced, means same amplitude, same frequency, but different in phase and by 120 degrees to each other. Okay, so this is the simulation is performed where the simulation is performed using the continuous mode. So means your calculation using the simulation will be updated for very small sampling period. So means the operation of the simulation, we can say that it's performed as analog operation, analog. So mean maybe you generate the sine wave using analog IC and the operational amplifier circuit or MIC. Analog, so mean the operation is continuous. So mean we can say that the calculation or the generation of the waveform will be updated for very small sampling time. Okay. Okay, but in digital implementation, so all the calculation will be in discrete mode, or we can refer as discontinuous mode. So mean your generation of sine wave, VA, VB, VC will be updated every sampling period. Depends on your clock frequency of the microcontroller. Okay, so mean for the discrete, so mean this is for the digital implementation, digital operation. So then you can notice by comparing between these two waveforms, you can notice that the sine wave shape for discrete mode. So where your sine wave shape in staircase, wave shape, ada bentuk tangga. So mean it will sample and hold for every sampling period. It depends on your clock frequency of the microcontroller. Okay, so this is VA, VB, VC. Sorry, this is the triangular wave shape. So because for sinusoidal modulation to generate the switching state, you need to compare the modulating signal VA, VB, VC and a triangular waveform. So this is triangular waveform, V triangular. So same goes to here, V triangular. So the red color is VA, the yellow is VB, the blue is VC. Okay. Okay, so maybe we can illustrate how the implementation of the modulator in digital implementation. So where you can notice the model signal, the data will be updated for every TS or sampling period. So that's why your modulator plot the wave shape of the modulator in staircase mode. Sorry, the staircase wave shape. Yeah. So actually you can see this wave shape through simulation. So maybe I can provide the simulation file that I upload to the file in Microsoft Teams. Then you can try explore and try yourself to understand how the simulation is modeled. Okay, so here you have three modulating signal. Then these three modulating compare with a single carrier or triangular waveform to generate the switching state. So maybe we can say that the modulating signal for the discrete mode, the modulating signal, modulating signals, which are VA, VB and VC are sample for every TS. Okay. Okay, then we move to the next page here. So this still in conventional inverter using the sinusoidal pulse width modulation. So actually this is a revision. So in order to plot or generate the switching state for controlling all switches, so means here, okay, so here is VA, VB, and VC. So let's say we try to analyze for this interval, okay, interval. So maybe green color ni. Okay, maybe we can analyze this region or this interval. Okay, so means for this interval, we try to analyze this interval. So for this interval, you can observe that the red color, the VA, is the highest, right? VA is the highest. Then the yellow color, almost zero value. Is it right? Then you have the blue color, which is VC waveform in negative value, is the minimum value. Okay, so mean we try to analyze for this interval, then we try to sketch here. Clear? So you have straight line. You cannot consider the wave shape is plotted using continuous mode, because the waveform is continuously changed and dynamically changed. So that's why in order to analyze the operation to generate the switching state, so you have to consider the the generation of the sine wave must be in discrete mode, discontinuous mode. So mean at one sample or for this interval, so then you get straight line wave shape for VA, VB, and VC. Clear? Nampak? Maksud dia, you consider your punya simulation, all the wave shape is plot using discrete mode or discontinuous mode. So mean you have sample and hold. So that's why your VA, VB, VC is plotted in staircase wave shape. So by considering for this interval, so then you get the three wave shape VA, VB, VC is in straight line here. So you have the red color is VA, the yellow color is VB, the blue is VC. Okay, so this is the triangular. This is the triangular waveform. Okay, so then to generate the switching state, so here this one is SA1, the top switch for leg number 1, and the top switching state for leg number 1. So then you can we know that for SA1, SA1, so the value of the switching state can be either 1 or 0. So means 0 or 1. So the value is 1 if what? VA is larger than or larger or equal to V triangular. Sorry, V triangular. Clear? So the value will be 0 if VA less than triangular. So mean that here I put otherwise. So then you can compare between these two wave shape, VA and triangular. When your VA is larger than triangular, so mean SA1 will be 1. Clear? Ini senang kan? But when your VA is less than triangular wave shape, V tri, so the switching status is 0. Clear? Okay, for SB1, so this is SB1, the top switching state for leg number 2. Clear? SB1, yellow color. Then for the blue color, you compare the blue wave shape, VC and triangular. So when your VC is larger than triangular, the SC1 will be 1. Otherwise, it will be 0. It's basic. You kena tahu before we proceed to the Z source. Z source. Yeah. Maybe your final exam, you must able to sketch the switching state waveform. Very important. So this is for the case of sinusoidal. For the Z source, you must know how to sketch the switching state. Okay, this for the switching state for the top switches. For every leg number 1, leg number 2, leg number 3. For the bottom switching state, so means here will be, sorry, SA1. SA1, SA2, sorry. So if I put subscript number 2, so means refer to the bottom switching state. So mean you can notice here the SA1, sorry, the SA2 wave shape, waveform, is actually is the inversion of SA1 waveform. Clear? So when your SA1 is 0 here, here will be 1. Otherwise, when your SA1 is 1 here, so SA2 will be 0. So mean the switching operation is complementary. So this is for SB2, the switching state for leg number 2. Then here will be SC2. Okay, clear? Okay, this basic, just revision. So you must also know how to sketch, to design the PWM circuit. So means this PWM circuit is responsible to generate the switching state, SA1, SA2 until SC2. So remember the sinusoidal pulse width modulation, the generation of the switching state is based on comparison between the modulating signals and a single triangular wave shape and triangular waveform. Okay, here, clear? So mean you can, for example, to generate for SB1 here. So SB1 will be, it can be either, ini sama cerita kan, 1 or 0. If your VB, right? Your VB, the modulating signal of VB is larger than or equal, depends on this relational operator here. Larger than or equal to triangular waveform. Okay. Otherwise, it will be 0. Okay. Ini dah buat dalam lab kan. So SB1 for control the top switch in leg number 2. For bottom switch, SB2, so you need to put the NOT gate to invert the signal. Okay, so mean actually you can construct this PWM circuit based on the waveform here. Okay, the above waveform. Clear? So you refer from this waveform, so actually you can construct the PWM circuit. Okay, clear? So it means here, okay, one thing you need to take note that the relational operators. So this is the relational operator here. So note that the relational operator, so you have 2 input, right? So actually you can set this operator either larger than or equal, smaller than or equal, or larger than. So you can double click this block using the Simulink MATLAB to change the operator. For this case, we use larger than and equal. So the output here, so you have single output and 2 inputs. Okay, so this is the input 1. Here will be input 2. So in order to produce output, value is 1 or 0. So 1, the production is 1 if first input must be first input. So you need to take into account. The first input must be larger than or equal, depends on the operator here. Larger than or equal to input 2. Otherwise, the value is, the production is 0. And the output of the relational operator will be 0. Clear? Simple. Kita kena tengok yang basic. We need to look at the basic operation before we proceed to the Z source. Okay, any question? Tak banyak slide pun ni. We have only 1, 2, 3, 4, 5, 6. Only 6. Yesterday 8 pages. Today 6. So means for Z source topic, we just only have 8 plus 6. 14 pages only. Okay, so you know, okay, make sure you know how to sketch the wave shape here, the generation of the switching state based on comparison of modulation and triangular. Then you need to know how to sketch the or construct the circuit. Okay. Then we move to the Z source. Okay, for Z source. Okay. So remember for Z source, the inverter, the Z source inverter allow the top and bottom switches can be turned on at the same time in one or more leads. Okay. So in order to operate or to make it your top and bottom switches turn on at the same time, so you need to introduce two constant signal. So we define the two constant signal. Okay, sorry. Two constant signal. So this case you need to introduce for Z source we have additional signal. So we refer as constant signal. Constant signals. So where you have two VP and VN. VP and VN, their value, sorry, they have same magnetic values, but different in sign. And the VP, the magnetic value of VP and VN, it cannot be larger than peak of triangular. So you have peak of triangular here. So this is the peak of triangular, ni. And the black color. So where the peak value is 1. For example, this value, sorry, maybe I use blue color here. 1. So mean your triangular varies between 1 to -1. Betul. So mean your peak of triangular is 1 volt. Peak to peak is 2 volt. Betul. Peak to peak of the triangular wave shape is 2 volt. So where your VP, it cannot be larger than 1. So mean your VP, these two values, constant signal, they have same magnetic value but different in sign. So means your VP, for example, you can set 0.8 volt. And VN should be what? Minus 0.8 volt. Same magnitude but different in sign. And your VP cannot be larger than 1. VP cannot be negative. VN, okay, negative. You can take into account these two, the constant signal. So you need to introduce, for the Z source, we have to introduce constant signal waveform, VP and VN, in order to generate the shoot-through. Shoot-through incident, shoot-through cases. Okay. So mean for this case, your VP here, this is your VP, right? And this will be your VN. So remember, VP cannot be larger than peak of triangular. Cannot be larger than 1. So this is positive. Okay. Here will be 0. Okay. So let's say same story. We try to analyze for this interval. So actually you can pick any interval, anytime. So for this case, I analyze this interval. Maybe I use, yeah. Okay. So the red color is the highest. Then you have yellow and blue. So maybe here. Okay. And this. Okay. Nampak tak? Ataupun aku tukar colour lain. I use different colour here. So we try to analyze for this interval here. Okay, by analyzing this interval, so actually you can notice that the rate VA waveform is the highest, right? Then the yellow color, almost zero voltage. Then the blue color is the minimum, right? So then you sketch here, VA, VB, VC, right? So means the green color here above the time axis will be VP. So this is the VP. Here will be your VN. VP and VN. So maybe we try to magnify the interval. So this is the zoom image. Zoom image for the interval. Zoom image. Okay, we focus on this interval. So the red is highest, then the yellow, and the blue color is the minimum value. Okay. So maybe you redraw by focusing for this interval. Okay, then okay, so this the switching state here actually is for the conventional inverter using the sinusoidal pulse width modulation. Clear, betul eh? So when your red color is larger than triangular, SA1 will be 1. Otherwise, when the VA is less than triangular, switching state will be 0, right? So how about the Z source? Okay, for the Z source, okay, so maybe you need to write here. Okay, Z source, Z source. So maybe I put the note here. All switching state, all switches, not are turned on or switch on, are turned on if your triangular waveform is larger than VP. So that's why we need to introduce the constant signal VP and VN. VP, or if the triangular wave shape is less than apa? VN. Okay, note that VP is equal to minus VN. If your VP is 0.8, so mean your VN will be minus 0.8. Okay. 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 Based on this statement, so you need to modify the switching state waveform here. So this switching state waveform is actually the production from the conventional inverter using sinusoidal pulse width modulation. So for Z source, you have shoot through incident. So you need to modify the switching state waveform to indicate the shoot through incident. Okay, so you have two cases so that your all switches can be turned on at the same time. One, when your triangular is larger than VP, another one is triangular less than VN. Okay, you have introduced the signal for VP and VN, the green color wave shape and the green color. Okay, so now we apply this statement or condition. So the triangular is larger than VP. So at which interval? So maybe I can highlight ataupun color this interval, right? Is it right? Where your triangular is larger than VP. First condition, triangular larger than VP. So mean you have this interval, then here, right? and also here. Is that right? This one. The first condition. Your triangular is larger than VP. So means you need to modify the switching state here. Macam mana badan ni? So mean here okay. Here 0, so you need to change to turn on. Here also turn on. Here will be turn on. So you need to modify the top switching status. Sorry, the top switching state for every leg. SA1, SB1, and SC1. So same goes for this interval. Right? Because originally the value is 0. Ni pun 0. Here also 0. Ni. This one, this interval also kan. Bottom switching state is okay. Because already 1. But for the top switching state, you need to modify. Because for the first condition, when your triangular is larger than VP, all switching states, all switches must turn on. Okay? So then here, you need to modify lah. From 0 to 1, here also from 0 to 1. 0 to 1. For the yellow the SB1, change from 0 to 1. So same goes to here. This one. For SC1, blue color. 0 to 1. Okay. So means for the first condition, when your when your triangular waveform is larger than VP, so all switching state are turned on. So you need to modify the switching state for controlling the top switches. Yeah. Okay, now how about the bottom switching state? So you need to look at the second condition. Okay, you have two conditions to be fulfilled. So one is triangular larger than VP, another one is triangular less than VN. Okay, then for triangular less than VN, so maybe I need to color this one first. So this is for the first condition. Okay, so for VN, what? VN larger than triangular. So means here, right? Is it right? Here also. So maybe you can extend here, color. Okay, now you need to modify the switching state for controlling the bottom switches for every leg. So mean here I erase first. This one also need to change the state from 0 to 1. Here is okay already, right? Sorry. Okay, then from 0 change to 1. Here also 0 to 1. SB2. Bottom switching state in leg number 2. Blue color. Okay. So the all switching state are turned on when first VP less than V triangular or VN larger than triangular. Tengok balik. bateri. Ini tak sampai. Okay, please check. Is it true? Is it correct or not? Mana positif gitu? Ini tak masuk. Ini positif. Okay, so this is for the second condition. All switching state are, sorry, all switches are turned on. Okay, any question? To make sure you know how to sketch the switching state. Okay, very important to answer the final exam. Maybe firstly, you can sketch the switching state waveform generate from the conventional inverter using sinusoidal pulse width modulation first. Okay. Hello, hello. Hello. Okay. Okay, next. Okay, so this area or interval, okay, this one here, here, here. So we can define the switching operation for this interval as shoot through zero state. Okay, shoot through zero state. Because all switches are turned on. Apa lagi nak buat? Okay, maybe we can have break for 10 minutes. Lama tak berehat eh. Weh, lambat ni. Tak habis juga ni. Okay, we proceed our class. So we have discussed how to sketch the switching state produced from the Z source inverter. So now how to construct the circuit, where the circuit is responsible to generate these switching states and this switching status. So actually you can start from the PWM circuit for sinusoidal pulse width modulation. And so this is the sinusoidal pulse width, the conventional method using the SPWM. Okay. So where to generate the states based on comparison between these three modern signal and a single triangular. So for the Z source, because you have the shoot through incident here, how to model, how to construct the circuit. So first of all, you need to erase. Okay, sorry, maybe you can start from, okay, you have, in order to design for to model for this condition. So the shoot through can be happen when, okay, maybe green color, VP VP is less than triangular, or VN larger than triangular. So you see the operator OR here. It can be either first condition fulfilled or second. So then it will produce 1. Okay, clear? So means here, you can start from here VP. So you have VP here. So maybe you can use constant block from MATLAB. So yeah, right. So green color. So this is the constant block. So the value you set as VP. Okay, then for the first condition, this first condition, VP should be less than triangular. So means, okay, so you draw the relational operator here, this block. So then you set this relational operator, so the operator will be larger than, right? And the triangular here, you obtain from the same triangular wave shape here. So this will be the first input. Yeah, maybe, yeah. Okay, sorry. So maybe I can change this operator to follow this condition kan. Sorry, so this you set as less than. So mean your first input should be VP, right? The first input should be VP. I move here, up here. So then the first input should be VP. Clear? So VP, you compare with the triangular. So this one is not connect. Then connect to the second input of the operator, right? So when VP is less than triangular, so then the output will be 1. So this will be 1. So this for the first condition, first condition here. Okay, for the second condition, you have Vn. So remember the Vn, it has same magnitude with Vp, but different in sign. Okay, so mean maybe you can multiply the Vp value. So you put the gain here. So this is the gain. And so in simulating block, you have the gain block, triangular wave shape, and triangular end. So then here you set the value will be -1, right? Okay, so this block is the gain block. In MATLAB, here is constant block. You can apply the constant block from the simulating library. So then the output of the gain will be Vn. So this is the Vn, right? Vn wave shape. Sorry, the Vn signal. Okay, then you can construct based on the second condition. So where the operator will be larger than. So the first input must be Vn. In order to produce the output here, so the first input must be larger than the second input. You can connect properly. The first input of the operator must be Vn. Second input from the triangular. Okay. Then the triangular will be second input of the operator. Okay, then you have the operator OR here. So should true can be happen when either one of the condition is fulfilled, because you have the operator OR there. Betul dia bukan and. Kalau and, two condition must be fulfilled. But this one is operator OR. So only one condition fulfilled, then the output will be 1. Okay, so means here, you can put the OR gate. Right? OR gate. Macam mana OR gate? OR gate symbol. So this is the OR gate. So then the output here, you can, firstly you need to erase this one first. Maybe you put the OR gate here. So you should put OR gate here. First OR gate. Is it right? Second. Siapa tak antik? You look it properly lah. Then OR gate here. So actually this is connect. This one connect to first input of the OR gate. Okay, then here you can connect directly to the second input for each OR gate. So mean this OR gate, first OR gate. Okay, here connect to here. This one is not connect. Okay, then you connect to the second input for each OR gate. So the output of the OR gate, sorry, this one also. So here will be what? SA1, SA2. So this is for the bottom, here for the top, for the leg number 2. Bottom switching state for leg number 2. Okay. So based on the waveform that we have sketched just now, so then you can refer to the waveform to construct the circuit. Okay. So you try to analyze. So in order to provide the shoot through incident, so you need to fulfill either these two conditions. Condition number 1 or condition number 2. Right. Tak betul. Oh ni. Okay, for this subject is not like high voltage subject. You need to memorize everything kan. We apply the concept for this subject. So that's why my notes full of picture, very technical. So that's why I try to reduce the scope and the content of the syllabus, so then we can focus on do more on technical and practical works. Okay, any question? Senang tak setakat ni? So far okay? So far so good? Good. Okay, then so this actually to compare, so you can try to compare like this page actually to compare lah the switching waveform, switching state waveform obtained from the conventional sinusoidal and Z source. So you can see the difference. So for the Z source, you have the shoot through incident. Clear? So of course you need to introduce the constant signal VP and VN for the Z source. For the conventional, it doesn't have the VP and VN because the switching operation is complementary. Right? So then here is the logic circuit, sorry, the PWM circuit for the conventional versus Z source. Right? So that's why saya try to use different color, the green color, in order for you to differentiate what is the modification has been made from the PWM control circuit. Clear? So now, last page. Last page. Okay, so yesterday we have derived some equation here, right? To verify that the G term, we define it as a boost factor, where this term is responsible to boost the voltage. So remember the G value must be larger than 1. It cannot be less than 1. Okay. So you can see here the G. So where the G boost factor, it depends on the ratio between shoot through period and sampling period. Nampak ni? You have this term. Mana ke? Ni. So how to relate the constant value Vp and Vn? What is the relationship between the time, the shoot through time, the Vp and Vn and G? Kita nak tahu apa, what is the relation between G and Vp and Vn? How how the constant values can determine the G? Faham tak? How the constant value can determine the desired G? Okay, so for this case, we have to analyze this page, this section. But you tengok the relationship between the delta, the ratio ni, the ratio period, Vp and Vn. So we have draw the switching state waveform here. Nampak? So let's say we just focus only one switching period. So where the switching period here, ni nampak? So this is what? TS. Switching period, right? From peak to the peak of triangular. Peak triangular here to the peak. So we define it as a period. So this time is the switching period or sample period. TS. Right? So remember your TS is the summation between the shoot through period plus non-shoot through period. Okay. Okay, so this is the TS from this point, this point to here, TS. So how about to here? The gap time here to this point. So this will be half of TS, right? Because your triangular is symmetry, ramp up and ramp down. The time taken for the triangular to change from the minimum to maximum is same from the maximum to minimum, reduced to maximum to minimum. So the wave shape is symmetry. So this is the triangular wave shape, and because ramp up and ramp down is the time taken is same. But for the sawtooth lain kan? Sawtooth maybe immediately increase, then ramp down. Immediately increase, ramp down. So this is sawtooth. For triangular here, and the time taken for increase minimum to maximum and maximum to minimum are same. So remember the carrier waveform you have two, triangular and sawtooth. Or maybe sawtooth can be ramp up, immediately reduce. Ramp up, immediately reduce. So this is the sawtooth. Okay. So means the time taken from this point to here should be 0.5 TS, right? Yeah. Okay, so remember your sampling period is summation between shoot through period and non-shoot through period. So can you identify at which interval we can define as a non-shoot through period? Ni. Saya dah tanda dah. So means here will be what? Non-shoot through lah. Shoot through here. Shoot through. So mean will be shoot through, right? But you need to divide by 4. So you can refer to this equation. For one sampling period from this point to here, so you have shoot through period and non-shoot through. So for one sampling period, you can notice you have 4 times or 4 interval for shoot through period. Okay? Ni kan? Here, so here, nampak you ada nombor 1, second, third, and fourth. So mean you need to divide by 4. Kan? So here also mana tadi? So this for number 2, shoot 2 period divide by 4. Here also shoot 2 period divide by 4. Here also shoot 2 period divide by 4. Betul kan? You kena refer to this equation. For one sampling period, TS, it is summation between shoot through period and non-shoot through period. So mean you kena tengok. For one sampling period, so actually you can have 4 times kan? Ataupun 4 interval for shoot through. Ni, I put number 1, number 2, number 3, number 4. So that's why you need to divide by 4. Agree? Senyap macam tak faham so you must divide by 4. Faham understand? Okay, so mean you divide by 4. Okay, so we consider you design the triangular wave shape, so it varies between +1 to -1. Yeah, clear? So mean dia punya peak triangular is 1, peak to peak is 2 volt. Okay, let's say, sebab kita nak derive the equation, the relationship between VP, Vn and delta. So means you can analyze for half of the sampling period. So let's say this form. Right? We just consider for half of the sampling period. Right? So mean you draw kat sini. So the triangular wave shape for half ni. So mean here, so the time gap here between these 2 points is what? TS divided by 2 kan? Ataupun 0.5 multiplied by TS. So where the value is changed from half of triangular -1 to +1. Right? From minimum to maximum. Okay, so you need to sketch the VP and Vn. VP is positive, Vn is negative, same magnitude. Okay, then you can label ataupun indicate the time information here. So you have here the gap between here we can define as change of y, because y-axis. Okay, so same goes to here. Change of y, because VP and Vn same magnitude value. So mean the gap for the top and bottom are same. Betul Sebab you kena tolak ni 1 volt dengan VP. So then you get the same magnitude value when you subtract between -1 and Vn. Clear betul So that's why you can write del y, change of y. Okay, so for the x ni, the gap here, you have the change of x. Here also change of x. And because the waveform is symmetry and the triangular wave shape is symmetry. So then you can have same gap size, change of x. So mean your change as x is what? So you refer from the ni. Change of x is TSH divided by 4, right? Betul Change of x ni change of time lah. So mean your shoot through time you must divide by 4. You divide by 4. So mean here change x. So mean here the change of x you can define here, right? Or also this interval change of x. So where the value is TSH divided by 4. Right? So mean you boleh put here as the shoot through period divided by 4. So same goes to here. Sekarang ni objektif kita, we want to get the relationship between delta and VPVN. Okay, then from here, okay, you need to apply ni. Apply rule of proportion. Apa bahasa Melayu dia? Someone can ni. What's in bahasa Malaysia? Rule of proportion. Perkadaran, perkadaran. Nisbah dan perkadaran kan. You belajar in mathematical kan. Engineering. Apply rule of proportion. So from here you can relate half of sampling period ni TS divided by 2 ni. So you can relate with y value, the change of y. So mean for the maximum variation from minimum here to maximum here, where the change of x is TS divided by 2. So how about the change of y here? So you akan dapat ni tu tak? For TS double 2, dia relate dengan this gap. Right. So where this is peak of triangular, peak to peak of triangular. Maksud dia 2 multiply by VTRI peak. Dan sebab you punya 0 here. Here is the peak of triangular. Ni, cursor saya ni. So mean you nak dapat maximum positive to minus. So this is the peak to peak. So mean you need to multiply 2 and V try peak. Clear? Betul? So mean here you can relate half of sampling period with 2 V try peak. Clear? And apa lagi satu? And you can relate what? Change of x ni, change of x. So where the value is shoot through period divided by 4. So it proportion to what? Change of x and change of y lah. Right, change of x is proportional to the change of y. Clear? So mean change of y. So this case change of y is you can calculate as what? V try peak. So change of y is the difference between peak of triangular and VP. Pandai pun. Or minus V try peak and VN. Good. So then from here, based on these two relations, so actually you can write. Okay, therefore, 0.5 TS by 0.5 TS. So then you can equate to 2 VTRI peak. Then here you divide. So this is shoot through period divided by 4. So then here will be change of y, right? Ini rule of proportion, nisbah dan perkadaran. Okay. Okay, then from here you can simplify this equation so that you have TCH divided by TS. Here change y, peak of triangular. Okay. Or this actually is change of y is peak of triangular subtract with VP divided by peak of triangular. So means the ratio between the shoot through period and sampling period is delta. So now you can relate the ratio sampling period, so shoot through period, delta and VP and VN. Nampak Nampak betul aku ajar. Okay. Ada nak tanya? Any question? Okay, lama semua dah bosan ni. Okay, maybe saya just show for one question of ni tutorial. Sekejap saja. Okay, this question number 1. Okay, you can read this question. Okay, you have 3 part here. Firstly, you need to know how to draw the equivalent circuit for 2 cases, none shoot through and shoot through mode. Okay, so then you calculate the required fundamental component of the Z source. This one apa ni? Based on the information given, VDC is 100 volt, the motion index is 0.8. You need to calculate the fundamental component obtained from the Z source. Construct the control circuit and sketch. Sketch waveform is provided. Just sketch the circuit. Here. So the answer ni. Ini just saya copy paste that we have discussed yesterday ni. Just copy paste from the note. So first you need to sketch the equivalent circuit case 1 and case 2. Then provide the assumption. Then you analyze for 2 cases. Get the inductor voltage, the inverter voltage. Lepas tu you obtain the equation here. Then obtain the equation of the peak of the inverter. Then finally you verify lah the term of G term played important role to boost the voltage. G. So where G you can state the equation is ni. Okay. So you define the ratio shoot through period and TS as delta. Okay. So then we know that for the conventional SPWM, the fundamental straightforward ni, MI multiplied by half VDC, equation number 9. But for the Z source, there has additional term G. Apa Okay, yang tak ada apa yang kita dah discuss. Okay, then part C. Okay, macam mana nak obtain ni? How to calculate the G? Ini jawapan ni. Saya ada buat ke? Ni, answer. Okay, to calculate the G, okay, so first you kena write the equation. Sekejap saya buat ni. Ni asal tak ada? Kenapa tak keluar pen? Nak suruh balik cepat ni. G is, ni. Sekejap je. 2 shoot to period divided by sampling period. So where we can write G as 1 divided by 2 delta. Okay. So then delta, so actually delta is shoot to period divided by sampling period. So from here you can get what the value? Delta. How to calculate the delta? So you need to refer to this one. Nampak? So that is purpose why we need to derive this equation. And we try to relate delta and VP and VN. Nampak? So then from here you can calculate delta. So delta is the ratio between shoot to period and sampling period. Or you can write as the difference between peak of triangular and VP divided by peak of triangular. So in this case, we consider the peak of triangular is 1 volt. VP as given in the equation. So now you can calculate the delta. Okay. So mean here VP. Mana? So here V try peak VP divided by V triangular peak. So when you get what? V triangular peak is 1 volt. VP as given in the equation. VP is what? VP is 0.8. 0.8. Then divide by 1. So from here you get delta is 0.2. Fine? So then you can calculate the G. You substitute the delta. Okay, where delta is 0.2, then you get G is 1.6667. So G value much larger than 1. So this case is 1.6. So actually you can get G, you can increase the G value by controlling the VP. But VP. Okay. So then when you get the G, so then you can calculate the fundamental component. V1. V1 obtained from the Z source. So where you have the modulation index, right? You multiply with G, the boost factor, VDC, divide by 2. For Z source, you have additional term here. Okay? So means from here, sorry, your MI given is 0.8. Based on the question is 0.8. So G is 1.667. VDC is 100 volt, right? Divide by 2. So then you get V1 is 66.6667. Right? Okay. Okay, then you can, part C, you need to construct the circuit. So I just copy from Simulink MATLAB. Okay, this is for the question number 1. Okay, 950. Okay, let me demonstrate. After then we can finish. So here, the simulation. Okay, now this is the simulation. So you can notice here is the Z source. Okay, after this class, I can upload this file to the folder, Microsoft Team folder. So you have the DC voltage here. So VDC is what? We said VDC is 100 volt. Same in the question. You have the diode here. Okay. So this is the network, impedance network. You have the inductor, two identical inductor, two identical capacitor. Here is the inverter. Then we just connect to the passive load, R load only. So this is the PWM circuit. Nampak? So you can compare lah this model, the circuit that we have drawn just now. So ni. So here is the VP. Nampak VP? You multiply by -1 to get the VN. So you have the OR gate here. So then you have 6 OR gate to produce the switching status here. A1 until SC2. Okay, sama macam that we have discussed tadi. Okay, then we can try to simulate. So let's say based on the equation, we set the amplitude is 0.8 because your modulation index is 0.8. So mean your triangular, peak of triangular is 1. Fine, ini 1 So your frequency, maybe we set 5K. Here 5K. Okay, this one also 5K, I think. 5K. Okay, 5K. So this one also 0.8 because we need to set the motion index 0.8. Okay, now we can run the simulation. Okay, now 40% the progress of the simulation here. Okay. So now this is the waveform. Ini tak keluar ni. Okay ni. Okay, the top graph ni is the inverter voltage. So this one is the phase voltage. I just plot for one phase, A phase voltage only, VAN, because VBN, VCN same wave shape pattern but different in phase. So then here, kenapa tak boleh turun? Kenapa tak boleh turun? Aduh, pening lah. Okay, maybe I close. Okay, to verify the fundamental component. So I need to use the FFT analysis. Okay, here you need to select the right waveform, VAN. So we just analyze for 2 cycles of waveform, VAN, starting from 0.2 until 0 point something, 0.2 something. So then we click the display button. So then you can see the fundamental component is 66.63. Similar to the calculated value. And the calculation is 66.6667. Okay. So the error percentage less than 5%. So the result is acceptable. Okay. Okay, clear? So this is the frequency spectrum component. So you have the fundamental component and the harmonics. So we just interested on V1, the fundamental component. So I can provide this simulation, then you can study lah how I construct or model the simulation for the Z source. Okay, ada apa nak tanya? So tak ada. So for your homework, so please do question number 2. Ni question number 2. So next week kita discuss we can discuss for question number 2. Alright.